All right, let me ask you something. What if I told you that you could take a source of heat, we're talking a gas flame, solar energy, even waste heat from a factory, and use it to make something ice cold? Sounds like it breaks the laws of physics, right? Well, it's a very real technology. So let's dive into the fascinating world of absorption refrigeration.
Yeah, it's a total paradox, and that's what makes this so interesting. We all learn that heat makes things, well, hot. But in this system, heat is actually the essential ingredient. It's the engine that drives the entire cooling process. So you're probably asking, how on earth is that possible? And look, it's not some kind of magic trick. It's just some really clever chemistry and physics working together in this elegant, continuous cycle. Okay, so think about the fridge in your kitchen. You know that humming sound it makes? That's the electric compressor, and its job is to squeeze a refrigerant gas until it turns into a liquid. Well, an absorption fridge just gets rid of it, throws it out completely. In its place is a totally silent, heat-driven part called a generator. So you don't need a bunch of electricity for the cooling, just a source of heat.
So what's the secret? How do you get away with ditching that compressor? Well, it all comes down to a special pair of liquids. And honestly, this chemical duo is the heart and soul of the entire system. The system uses what's called a binary mixture. You can just think of it as a team of two liquids that have this really unique relationship. You've got the refrigerant, that's the one that actually does the cooling, and then you've got the absorbent, which is kind of like its carrier or its partner. A really common team-up you'll see is ammonia for the refrigerant and just regular water for the absorbent. And this is where it gets really cool. Imagine the water is like a chemical sponge. When it's cool, this sponge just loves to soak up the ammonia gas. I mean, it just drinks it right up. But then, when you apply heat, it's like squeezing that sponge as hard as you can. The heat forces the ammonia to literally boil right out of the water. This ability to absorb and then release, that's the engine. Okay, so we've got our magic chemical duo. Let's actually put them to work. The whole thing really breaks down into a simple, continuous 4-step cycle. Step 1 is the generator. This is where we bring the heat. We're squeezing the sponge here, boiling that ammonia out of the water, and that creates a high-pressure ammonia gas. From there, that hot, high-pressure gas travels over to the condenser. This is a lot like the coils you'd find on the back of a regular fridge. Its whole job is to let that heat escape, which cools the gas down until it turns back into a pure liquid. All right, now for the part where the magic really happens. The liquid ammonia flows into the evaporator. Here, the pressure suddenly drops, which makes the liquid instantly boil and turn back into a gas. This whole process of rapid evaporation literally sucks the heat out of everything around it. And that is what makes the inside of the fridge get cold. And finally, to complete the loop, that cold ammonia gas goes to the absorber. This is where it meets back up with our dry sponge, the water that was left behind. The water soaks it right back up, and the whole mixture is ready to go back to the generator and start the process all over again. So here you can see the whole thing laid out. Heat comes in at the generator, separating the two liquids. The refrigerant gas cools into a liquid in the condenser. Then it creates the cold in the evaporator. And finally, it gets soaked back up in the absorber to begin its journey all over again. It's just a beautiful, continuous, and totally silent heat-powered loop. But look, this isn't just some theory on a diagram. This technology is actually out there in the real world, and it's used in some pretty surprising places. Let's take a look at some actual machines. Now, in big industrial setups, things can look a bit more complicated. You can see they add extra parts like heat exchangers to try and squeeze out a little more efficiency. But don't let that fool you. At its heart, it's still doing the exact same thing with those same 4 key parts: the generator, condenser, evaporator, and absorber.
And this is really clever. For smaller units, like the kind you might find in an RV or an off-grid cabin, the whole system is designed so it has 0 moving parts. None. It just uses natural gravity and convection to circulate the fluids. That makes these fridges incredibly reliable and, of course, completely silent.
Okay, so at this point, you might be wondering, if this tech is so great, it's silent, super reliable, and runs on heat, why don't we have these in every kitchen? Well, like with everything in engineering, there is always a trade-off. The upsides are pretty obvious, right? With hardly any moving parts, they're simple to maintain and barely sip any electricity. But, and this is a big but, they have one major downside, and that's efficiency. And this really hits the nail on the head. The biggest drawback is efficiency. The source material talks about something called the coefficient of performance, or COP.
That's really just a fancy way of asking, for all the energy you put in, how much cooling power do you actually get out? And for these absorption systems, that number is pretty darn low.
So what does low mean? Well, their COP is typically less than 1. Think about that. That means you're putting in more heat energy than the amount of cooling you're getting out. Your standard kitchen fridge is way, way more efficient. And that really is the fundamental trade-off here. You're giving up raw efficiency to gain that incredible reliability and the unique ability to run on a heat source.
But that leaves us with a really interesting final thought. This technology is old, for sure. But what if that big weakness, the low efficiency, doesn't matter? What if your heat source is basically free? Like waste heat from a power plant or solar energy from the sun? All of a sudden, that inefficiency isn't such a big deal. So it makes you wonder, could this elegant, old-school idea from the 19th century actually be a key solution for our 21st century energy challenges? It's definitely something to think about.